Well, real. Physically, I mean, we kind of instinctively know the difference, right? Between, say, a solid baseball, you can track it, measure it, and maybe a ripple spreading across a pond. That's more like a diffuse disturbance, no single spot. Our everyday world trains us to put things in boxes, particle or wave. But what if, down at the very bottom, at the most fundamental level, that neat distinction just melts away? What if something could be both? A particle and a wave, depending on, well, how you decide to look at it. Today, we're doing a deep dive into one of the most, frankly, mind-bending concepts in all of physics, wave-particle duality. For centuries, classical physics had this solid foundation. Particles, they were discrete, little localized things. Definite mass, definite momentum, following predictable rules like Newton's laws. And waves, they were continuous, spread-out disturbances, defined by things like frequency, wavelength, amplitude, famous for interference, diffraction, all that wave stuff. Classically, an object was one or the other. Simple. It could not be both.
Right. And this view, the one that feels so right, so intuitive to our senses, it started to crack. Spectacularly, actually. New discoveries down at the atomic scale, things like the photoelectric effect or the weird way black bodies radiated heat, they just didn't fit the old rules at all. And these weren't just small puzzles needing a quick fix. These anomalies, they demanded a whole new way of thinking, or a revolutionary leap, really. So our mission here for you is to dissect the key equations that define this duality, explore the whole idea of the matter wave, and then crucially, look at the solid experimental evidence, the proof. Hopefully this gives you a deeper, maybe a more nuanced grasp of what reality actually looks like down there.
Okay, so if classical physics felt so solid, where did the first cracks actually appear? What were these anomalies that just completely stumped the scientists?
It was a fascinating time, almost like watching a scientific argument unfold. You had an accepted idea, the thesis, right? Then, bang, new evidence comes along that contradicts it, the antithesis. And out of that conflict, eventually, you get a new, better understanding, the synthesis. So for light, the main idea, the thesis, was definitely the wave theory. Huygens pushed for it. Thomas Young's double-slit experiment in 1801 seemed to nail it down. Waves explained everything.
Seemed settled then.
Until the photoelectric effect. That was the stark antithesis. It showed light behaving exactly like tiny, discrete particles or quanta of energy. And for matter, it was almost the reverse story. J.J. Thomson discovers the electron in 1897. Characterizes it as a particle. Definitely a particle. That was the thesis for matter.
Okay.
The antithesis came later. Experiments started showing electrons doing wave-like things, like diffraction, which everyone thought only waves could do.
So particles acting like waves, waves acting like particles. What emerged wasn't just splitting the difference, was it?
Not at all. The synthesis was this profound idea, wave-particle duality, a totally new paradigm, more abstract, where wave and particle aren't really what something is, they're more like complementary aspects. Two sides of the same quantum coin, like you said before, and which side you see depends entirely on how you set up your experiment.
Fascinating.
And the key number connecting all this, Planck's constant, usually written as h. It's this incredibly, incredibly tiny number. And that smallness, that's the critical reason why our big everyday world looks classical. It obeys the old rules perfectly well for us.
But the microscopic world.
The world of atoms and photons that operates by these new, strange quantum rules. It's amazing, really, how one tiny constant could fundamentally reshape how we see the entire universe.
So this duality sounds bizarre. How did physicists actually manage to put numbers on it? How do you quantify something that seems like a paradox? What are the sort of mathematical handholds here?
Well, it really boils down to two key relationships, two foundational equations. Think of them like, I don't know, a quantum Rosetta Stone, a dictionary that lets you translate between particle language energy, momentum, and wave language frequency, wavelength.
Okay, what's the first one?
The first is the Planck-Einstein relation. E equals hf, EHF. This started with Max Planck back in 1900. He was wrestling with black body radiation. Classical physics predicted something absurd, the ultraviolet catastrophe. Infinite energy at high frequencies. Obviously wrong.
Right.
Planck found he could fix the math, but only if he assumed energy came in discrete chunks, or quanta. He actually thought it was just a mathematical trick at first, a fudge factor almost.
He didn't believe it was real.
Not initially. But then Albert Einstein, in his miracle year in 1905, took it seriously. He proposed this quantization wasn't a trick, it was real, an intrinsic property of light itself. Light is made of these energy packets, which we now call photons. So EHF became the definitive link. Connecting frequency, a classic wave property, directly to energy, a classic particle property. You can also write it using wavelength, E-tube, or with angular frequency, and the reduced Planck constant, ATO. and get this, tying it to EFIO, show that even a massless photon carries an effective mass of MEO-Schaeffi, blurring that line even further between waves and particles.
Okay, so light, which everyone knew was a wave, sometimes acts like a particle. That's one side. But you mentioned the reverse. Did someone really propose that particles, like electrons, could act like waves?
That was Louis de Broglie's brilliant insight in his PhD thesis, 1924. A really bold move. He basically said, hey, nature loves symmetry. If waves can act like particles, maybe particles can act like waves. Maybe this duality thing is universal, applies to all matter.
So he just flipped the logic.
Pretty much. He looked at the photon's momentum relation and just proposed it should work the other way around for any particle, which gives us the famous de Broglie relation, lambda equals h divided by p AP, where p is momentum, usually mass times velocity, and v.
Lambda equals h over p.
And notice the relationship. It's inverse. The bigger the momentum, so the faster something moves, or the heavier it is, the shorter its wavelength. This is absolutely key. It explains why quantum wave effects are obvious for tiny things like electrons, but completely hidden for, say, us or a baseball.
Because our momentum is huge, so our wavelength is minuscule.
Exactly. Immeasurably small. And remember, de Broglie's idea was just a hypothesis at first. It wasn't proven until afterwards, when experiments like Davison and Germer showed electron diffraction, perfectly matching his prediction.
Incredible. So putting them together, EF links the wave's time aspect, frequency, to the particle's energy, and links the wave's space aspect, wavelength, to the particle's momentum.
Precisely, the two foundational pillars.
And that tiny number h, Planck's constant, is right there in both.
Always. It's roughly 6.626 times 10 to the minus 34 joule seconds. Incredibly small. It sets the fundamental grain size of the universe, if you like, the smallest unit of action. It pops up everywhere in quantum mechanics, Schrödinger's equation, Heisenberg's uncertainty principle. It defines the basic unit of angular momentum, too.
So we know its value very precisely.
Oh, yes, extremely precisely. But why it has that specific value? Why not something else? That's still one of the big unanswered questions in fundamental physics, a real mystery.
Okay, so these equations give particles a wavelength, a frequency. They connect the particle and wave descriptions, but it begs the question, doesn't it, for you listening?
Yeah.
What is this wave? What's actually waving when we talk about a matter wave? Is it like a water wave, something physically rippling?
That's the million-dollar question, isn't it? And the answer takes us deep into the weirdness, the abstraction of quantum mechanics. Enter Erwin Schrödinger, 1926. He developed the fundamental equation of quantum dynamics, the Schrödinger equation, and he introduced the wave function, usually written with the Greek letter psi.
The wave function, right?
Now, this f is a mathematical function. It's complex valued, which means it involves imaginary numbers. And the core idea, the postulate, is that this wave function contains all the information you can possibly know about a quantum system. Everything.
So it's like the quantum equivalent of Newton's laws.
In a way, yes. Just like F lets you predict where a classical object will go, Schrödinger's equation lets you predict how the wave function will evolve over time.
Okay.
And a really important feature is that the equation is linear. That mathematical property is the basis for superposition.
Superposition, meaning something can be in multiple states at once.
Exactly. A quantum system can exist in a combination of different states simultaneously, like an electron being potentially here and there at the same time, which is absolutely crucial for explaining things like the double-slit experiment we'll get to. Schrödinger's equation gave the dynamics, the how things change part, that was missing from de Broglie's original idea. Okay. It lets you calculate things like the specific energy levels electrons can have in atoms.
But the wave function itself, can we see it? Does it represent something physically real?
No. And this is where Max Born comes in, also around 1926. He provided the physical interpretation, and it was radical. Born said the wave function itself isn't directly physical. You can't observe it. It's not a wave of stuff like water.
So, what is it then, if it contains all the information?
It's about probability. The Born rule states that the square of the absolute value, or the modulus of the wave function written, xt, gives you the probability density.
Probability density,
meaning the likelihood of finding the particle at a specific position x at a specific time t if you were to measure it.
So it's not where the particle is, but where it might be.
Exactly. This was a huge break from classical physics, absolutely definitive. No more determinism. A quantum particle isn't at a definite point until you look. It's described by this cloud of probability. So the matter wave isn't a physical thing waving in space. It's more like a wave of information, a probability amplitude. And the waving isn't happening in our 3D space, but in an abstract mathematical space. Physicists call it Hilbert space. It's like a space of all possibilities.
And the patterns we see, like interference.
Those patterns are like the shadow or the projection of that probability wave onto our familiar physical space.
Okay, this is getting very abstract. But you said earlier, a theory lives or dies by experiments. So despite how weird this sounds, there must be solid proof, right? What are the key experiments that forced physicists to accept this strangeness?
Absolutely. The experimental evidence is undeniable, even if it feels paradoxical. We can kind of follow the story. First, nailing down light as a particle. That's the photoelectric effect.
One Einstein explained.
The very one.
Right.
Remember, by 1900, everyone thought light was definitely a wave.
Hmm.
Maxwell's equations, Young's experiment,
Mm-hmm.
case closed. But the photoelectric effect metals spitting out electrons when light shines on them showed behavior that flatly contradicted wave theory. Well, wave theory said any frequency of light, if it's intense enough, should eventually knock electrons out.
More energy in the wave, right?
Exactly. But experiments showed, nope, emission only happens above a certain specific threshold frequency for each metal. Below that, nothing happens, no matter how bright the light.
And Einstein's photon model explained that.
Perfectly. He said light comes in packets, photons, with energy, EF. To kick an electron out, a single photon needs enough energy to overcome the metal's work function, the energy binding the electron. If AFF is less than the work function, it doesn't matter how many photons hit, none have enough energy individually.
Okay, what else didn't fit?
Wave theory predicted that brighter light, higher intensity, should give electrons more kinetic energy when they come out, more wave energy hitting them.
That makes sense.
But experiments showed the maximum kinetic energy of the electrons didn't depend on the intensity at all. It only depended on the light's frequency.
Weird. How did photons explain that?
Simple. One photon gets absorbed by one electron. More intensity just means more photons, so more electrons get knocked out. But each electron still only absorbs one photon's worth of energy. The max energy an electron gets is the photon's energy minus the work function. Kmec is h of W. Higher frequency means higher energy per photon, so higher Ke.
And there were other discrepancies too.
Yes. Classical theory saw no reason for a linear link between electron Ke and frequency, but experiments showed exactly the Ke went up linearly with F. Again, Kmac's HFW explains it directly. And finally, wave theory suggested that for very dim light, there should be a time delay before electrons get enough energy to escape. Experiments showed emission was basically instantaneous.
Because the photon delivers its energy all at once.
Exactly, like a single concentrated punch, not a gentle push. So the photoelectric effect was ironclad evidence. Light acts like particles when it interacts with matter.
Okay, so waves can act like particles. Check. But the really wild idea was the reverse. Did they find proof that actual matter, like electrons, could act like waves?
They did. And that brings us to the Davison-Germer experiment, a beautiful piece of work. Remember de Broglie's hypothesis from 1924?
Yeah.
It was just an idea then, no direct proof.
Right.
Then, in 1927, Clinton Davison and Lester Germer were at Bell Labs firing beams of electrons at a nickel crystal target. And there was this lucky accident. Their vacuum chamber broke, air got in, oxidized the nickel surface. To clean it up, they heated the nickel strongly.
Okay.
That heating process, serendipitously, annealed the nickel. It reformed the surface into large, perfect single crystal regions. Before, it was likely many small crystals jumbled together.
And that made a difference.
A huge difference. When they started the experiment again with the annealed crystal, they saw something amazing. The scattered electrons weren't just coming off randomly. They showed distinct peaks in intensity at very specific angles.
Peaks.
Like diffraction patterns. Exactly the kind of patterns you get when waves like X-rays scatter off the regular atomic layers in a crystal. It was the undeniable signature of wave behavior.
For electrons, which they thought were particles.
Precisely. And the numbers matched beautifully. They calculated the expected de Broglie wavelength for their electrons based on the voltage they used, which sets the momentum. For one prominent peak, they predicted about 0.167 nanometers.
And what did they measure from the diffraction pattern?
About 0.165 nanometers. The agreement was stunning. It proved de Broglie right. Electrons do have wave properties. Matter acts like waves.
Wow. So photoelectric effect shows light acting like particles. Davison-Germer shows particles acting like waves. Is there an experiment that shows both aspects, like in one go?
Ah, yes. The absolute classic. The quintessential demonstration of duality, superposition, probability, all of it. the double-slit experiment.
This is the really famous one, isn't it? How does it reveal the heart of the mystery?
It truly does. The setup is simple conceptually. You have a source shooting out particles, electrons are a great example, then a barrier with two narrow parallel slits. And behind that, a detector screen that shows where each electron lands.
Oh.
Now, if you shoot a whole beam of electrons through, with both slits open, what you see on the screen is not just two bright bands corresponding to the slits. You see a pattern of alternating bright and dark stripes. Fringes.
Interference.
Exactly, the classic hallmark of waves interfering with each other, like light waves or water waves passing through two openings. So, conclusion. Electrons are behaving like waves.
But wait, electrons are particles, right? They hit the screen one by one.
Precisely. And here's the mind-blowing part. Turn the beam intensity way, way down. So low that only one electron goes through the apparatus at a time. Like, electron number 1 goes through, hits the screen, then electron number 2, and so on.
So you track each individual hit.
Yes. And each electron arrives at the screen as a single, tiny dot. A localized impact. Undeniably particle-like behavior.
Okay, so they are particles.
But, and this is the deep paradox, let those single particle impacts build up over time. Thousands of them. What pattern do they form collectively?
Don't tell me.
The exact same interference pattern of bright and dark fringes you saw with the beam.
How is that possible? Each electron went through one at a time.
It implies that each individual electron, somehow, goes through both slits simultaneously.
Right.
As a wave, it interferes with itself, and then when it hits the screen, it manifests as a particle at just one point.
That's just deeply weird.
It is. The wave function describes this probability wave spreading through both slits. The interference pattern reflects the regions where the probability of detection is high, bright fringes, or low, dark fringes.
And what happens if you try to catch the electron, figure out which slit it actually went through?
The which-way experiment. If you put detectors right at the slits, detectors that can tell you, okay, this electron went through the left slit or that one went through the right slit.
Does the interference pattern change?
It completely disappears,
Yeah.
vanishes. What you see on the screen then is just two broad bands, exactly what you'd expect if classical particles were just piling up behind each slit.
Just by looking. Essentially, yes. The act of measuring which path the electron takes forces it to behave like a particle at the slits, destroying the wave-like superposition needed for interference. This is called complementarity. You can see the wave nature or the particle nature, but not both in the same measurement setup.
So the measurement itself changes the outcome.
Fundamentally. And it's not about physically bumping the electron clumsily, it's about information. Gaining that which-way information inherently destroys the wave interference. It's a process called decoherence. So yeah, the double slit is the ultimate quantum magic show. It reveals the probabilistic nature, superposition, and the absolutely critical role of measurement, all in one experiment.
Okay, if this wave-particle duality thing is universal, applying to electrons, photons, everything, why don't we see it in everyday life? Why doesn't a baseball diffract when I throw it through a doorway? It seems like there's a huge disconnect. That's a perfectly reasonable question. And the answer lies back with de Broglie's equation, the wavelength. You can think of the de Broglie wavelength as a kind of quantumness meter. The key thing is how big that wavelength is compared to the size of the object itself, or the size of things it interacts with, like the doorway.
So size matters.
Size and momentum, yes. When the wavelength, lambda, is roughly comparable to, or even larger than, the relevant dimensions like the spacing between atoms in that nickel crystal for the electron, then wave properties dominate. You see quantum effects like diffraction and interference.
But for big things.
For macroscopic objects like baseballs or even dust motes, the de Broglie wavelength is vastly smaller than any physical dimension we can perceive or interact with. In that case, the object behaves classically. For all practical purposes, the wave nature is completely hidden.
Can we put a number on that baseball example?
Sure. So let's take a standard baseball, about 0.145 kilograms.
Okay.
Throw it at, say, 90 miles per hour, which is roughly 40 meters per second. Its momentum, PMV, is about 5.8 kilojoules. Now plug that into OPS, using Planck's constant, H-Perry 6.6 by 10 iones.
What do you get?
You get a de Broglie wavelength of approximately 1.1 times 10 to the minus 24 meters.
Minus 34, that sounds small.
Astoundingly small. That's about 19 orders of magnitude smaller than the diameter of an atomic nucleus. It's just unimaginably tiny.
So to see diffraction, the doorway would need to be that small.
Exactly. You'd need an opening comparable in size to 10 U-meters to see the baseball diffract.
Yeah.
Which is, well, physically impossible. Look at some comparisons. An electron moving at 10% the speed of light has a wavelength around 24 picometers tiny, but comparable to the space between atoms. easily observable wave effects, a proton at that speed. About 13 femtometers comparable to nuclear sizes, important in nuclear physics. Even something big like a buckyball molecule. C60, its wavelength is much smaller than its diameter, but scientists have actually measured interference patterns for buckyballs, pushing that quantum boundary.
But the base
At 10% light speed, its wavelength would be around 10 Uri meters, about 10 to the 25 times smaller than a proton. Utterly negligible. Unobservable wave effects.
So it's the sheer mass of everyday objects compared to the tiny value of Planck's constant that washes out the quantum weirdness for us.
Precisely. It becomes completely irrelevant on our scale. This is a great example of the correspondence principle in physics. The idea that quantum mechanics has to reproduce the results of classical mechanics when you get to large enough scales. And it does.
Okay, so duality isn't just some weird footnote for tiny particles. It's fundamental, even if hidden from us. You said it has deep consequences. What are some of the big ones that reshape how we think about the physical world?
Oh, absolutely. It's not just philosophical. Take the Heisenberg uncertainty principle, 1927.
The one that says you can't know position and momentum perfectly at the same time?
That's the one. And it's often misunderstood. People think it's just about limitations of our measuring devices, like our ruler isn't good enough, or measuring position bumps the particle and changes its momentum.
It's not just about clumsy measurements.
No, it's much deeper than that. It's an intrinsic property baked into the wave nature of matter itself. Think about waves. To make a wave that's very localized in space, a sharp wave packet, so, its position accurately, small x, you have to pile up lots of different sine waves with different wavelengths.
Okay.
But different wavelengths correspond to different momenta. So if you use many wavelengths to pinpoint the position, you automatically introduce a large spread, a large uncertainty in the momentum, large back.
And the other way around, if you want to know momentum precisely.
To have a well-defined momentum, small nap, your wave needs to be made of a very narrow range of wavelengths, almost a pure sine wave. But a pure sine wave is spread out all over space. It's not localized at all. So you have a huge uncertainty in position, large max.
So you can't have both sharp position and sharp momentum.
Never. There's an inescapable trade-off built right into the wave description. The math works out to x times app has to be greater than or equal to Planck's constant divided by 4. Here's it 2.
The uncertainty product has a minimum limit.
Exactly. A fundamental fuzziness imposed by nature itself. You simply cannot prepare a quantum state that has both a perfectly defined position and a perfectly defined momentum. It's a direct result of wave-particle duality.
That's profound. What else comes out of this wave nature?
Quantization. The fact that things often come in discrete amounts in the quantum world. Think back to the Bohr model of the atom, 1913.
He just kind of declared that electrons could only be in certain orbits, right, with specific energies and angular momentum.
He did. It was an ad hoc rule, meaning he put it in specifically to make his model match the experimental data for hydrogen's light spectrum. He didn't really have a deep reason why those orbits were special.
But wave-particle duality provides the reason.
Yes. De Broglie and Schrödinger showed that Bohr's quantization isn't arbitrary at all. It's a natural consequence of the electron behaving like a wave trapped inside the atom.
How does that work? Trapped waves.
Think of a guitar string, fixed at both ends. When you pluck it, it doesn't vibrate at just any frequency. It vibrates at specific frequencies, the fundamental note, and its harmonics, or overtones. These are standing waves.
Waves that fit perfectly onto the string.
Exactly. An integer number of half wavelengths has to fit on the string length. Now, think of the electron orbiting the nucleus. It's trapped by the electrical attraction. Its matter wave is confined to an orbit. For that wave to be stable, for it to be a standing wave around the nucleus, it has to fit perfectly. An integer number of its full wavelengths must fit exactly into the circumference of the orbit. So n times lambda must equal 2 pi r.
Okay, n wavelengths fit in the circumference.
Now, substitute de Broglie's relation, or HMV, you get n times equals 2 to 4.
NHMV.
Equals 2NV.
Rearrange that equation.
Multiply both sides by MV and divide by 2. What do you get?
MVR n times H over 2.
Exactly. MVR NH2 over.
Right.
Or, since H2 is written as n bar, you get MVR n yoja. And MVR is the angular momentum, L. So LF.
That's Bohr's quantization rule.
Precisely the rule Bohr just had to postulate. It emerges naturally from treating the electron as a confined wave. Quantization isn't some weird extra rule. It's just the natural harmonics of matter waves trapped in systems. It's the music of the atom played on wave strings.
That's incredible. It ties it all together. So, wrapping this up, wave-particle duality isn't just strange. It's one of the absolute cornerstones of modern physics, isn't it? A complete shift from how we used to see the world.
Absolutely. It marks that definitive break from the old classical deterministic view. It ushered in quantum mechanics, probabilistic, strange, yes, but incredibly powerful and predictive.
And it's not just a vague idea of things being both. It's mathematically precise.
Rigorously quantified. Planck's EHF, de Broglie's Abuti,
Yes, right.
with H setting the scale. And the whole theoretical framework built around Schrödinger's equation and Born's probability interpretation works stunningly well.
And it's not just theory. As we discussed, it's backed by solid, undeniable experiments.
Incontrovertible results. The photoelectric effect, light as particles. Davis and Germer, matter as waves. And the double-slit experiment, showing both aspects in action and highlighting that crucial role of measurement.
It's not just for physicists in labs either, is it? This stuff has real-world impact.
Immense practical legacy. Electron microscopes that let us see things on the atomic scale. They rely on the wave nature of electrons, semiconductors, transistors, the chips in every phone and computer. Their design is fundamentally based on the quantum behavior of electrons in materials. Lasers, too. And of course, the whole developing field of quantum computing is built directly on these principles of superposition and entanglement, which stem from this duality.
So it's everywhere in modern tech. And yet, despite predicting things so accurately, despite enabling all this technology, the deep questions remain, don't they?
These certainly do. What is reality fundamentally? What does measurement actually mean? What's the role of the observer, if any? These philosophical questions, sparked by duality over a century ago, are still debated, still fascinating.
It feels like quantum mechanics gave us incredibly powerful rules, but maybe also showed us the limits of our everyday intuition when it comes to grasping reality's deepest secrets. It definitely makes you rethink what solid or real even means, something for you, the listener, to ponder.